we left off talking about reactions. So let's just go through a brief review. We had the metathesis reactions first. So the metathesis reactions dealt with ion combinations, and it doesn't always have to fit this form, but one of the forms is double replacement. There are other forms, you just take the ions and combine them, and so just etc. It could be in any form, so you're just looking for ion combination. And then the second type of reaction that we're looking at for acid-base. The acid-base reactions, we only looked at Bronsted acid-base reactions. Bronsted acid-base reactions are termed proton transfer. Where we take a proton from the acid, give it to the base, and the base takes a proton from the acid. But we also have another type of acid-base reaction called Lewis. Lewis looks at acids and bases a little differently. There's electron pair donors and electron pair acceptors, but we aren't going to get into Lewis. This will come later on. So we just focused on Bronsted proton. And then the third type of reaction that we looked at are redox reactions or oxidation reduction reactions. For redox reactions, we looked at different subcategories of this. One was the element plus element. If you take two elements, you can get them to react to form some kind of compound here. So an element plus element yields compound type reaction. You could actually take multiple elements. It doesn't have to be a binary compound. It could be 3-element compound or 4-element compound. So this is just element plus element compound. So one element might be a metal. Metals lose electrons, form cations. The other might be a non-metal, which gains electrons to form anions. So we could figure out the charges based on the periodic table, or what, if it's variable charge, what its most common charge might be, like copper 1 or copper 2, it's copper 2. And so element plus element. Going forward here, we form a compound. We can also take a compound and decompose it into elements. And so forward is combination, reverse is decomposition. But we have other types of combination decomposition. You know, ion combination, that's metathesis. And so just because it's a combination doesn't mean it's redox. It could be a metathesis, but it could be acid-base, or it could be redox. So combination in itself is not a unique category. And so that's element plus element. Then we had single replacement. Single replacement follows the form A plus BX. Get that. And then we have the combustion reactions. For combustion reactions, we're typically taking like a hydrocarbon or a carbon, hydrogen, oxygen containing compound. So hydrocarbon just consists of hydrogen and carbon. A carbon, hydrogen, oxygen compound could be a sugar, could be an alcohol, could be an ether, and so there could be many different categories of that. But if we take our CH or CHO compounds, I'll put O in parentheses here, and then combust it in O2, we're going to end up with the same products, whether it's an alcohol or hydrocarbon or whatever. And what are the products of combustion? Products would be CO2 and water. So if we just burn it, we'll form CO2 and water. And so we just balance it. This would be for complete combustion. We assume complete combustion. Complete combustion.
it doesn't have to be complete combustion. We could form carbon monoxide, we can form soot particles. That would be incomplete combustion. But for purposes of predicting the products and balancing, we'll assume it goes all the way to CO2. That's combustion. Another type of setup that we have for redox uses the chart. We just termed it the chart method. And so here we just, pick the strongest, react the strongest together, and then determine if there's a driving force present. Determine driving force. Now, just because we have the strongest pair of reactants, the strongest oxidizer and the strongest reducer, doesn't mean a reaction is going to occur. There has to be a driving force where it goes from stronger to weaker. And so we do the strongest, then determine the driving force. This is a chart method. Okay, so we spent some time looking at the chart method. We haven't gotten really to the skeleton redox yet, so that's what I'm going to talk about today, skeleton redox. For the skeleton redox, the purpose is different. For skeleton redox, we need only to complete and balance here. We do not predict the products. We do not predict products. The major products would be given in skeleton redox. And skeleton redox comes about because reactions are kind of complicated. Reactions depend on a lot of variables. We can make predictions like this. For example, we could use the chart to make predictions of chemical reactions, but when we use the chart, we have to play by the chart's rules. Well, what does that mean, playing by the chart's rules? What that means is that we have to restrict the playing field. How do we restrict the playing field? Well, if you take a look at the oxidation reduction chart here, and look at the footnote. You see the footnote down here? There's a footnote that says here. If you take a look at that footnote's going to be the restrictions there. The footnote says that we're going to restrict the concentrations and the pressures to 1 molar and 1 atmosphere. What happens is if you start playing around with the concentrations and you start playing around with the pressures, you might not get what you expect to get. Also the temperature. The chart is fixed at 25 degrees C. So when we use the chart method, we're kind of constrained to 25 degrees C, 1 atmosphere, 1 molar. However, if we want to change those conditions, it might screw things up, and we might not get what we think. And so the best thing is to learn and understand reaction chemistry based on the chart's restrictions, and then we can make some predictions based on what we expect to happen. For example, if we go more concentrated, things typically become more reactive. If we go less concentrated, they typically become less reactive. And so we keep these types of things in mind. Temperature has an impact as well. And so for skeleton redox, there are many variables here in chemical reactions. But when we have many variables, it's hard to predict. And so let's say I want to burn my methane at the exact conditions that gives me, let's say, 75% carbon dioxide, 25% carbon monoxide. Or let's say I don't want any carbon dioxide, I just want carbon monoxide. I'm worried about greenhouse effects, so let's get rid of the CO2 and replace it with CO. Is CO greenhouse gas? Or is it just CO2? CO. CO would also actually turn out to be a greenhouse gas, so that wouldn't be very effective. But anyway, let's say I wanted to burn this, so I got all carbon monoxide. Well, tell me what conditions I need to do that. Is that so easy to do? Easy to predict? No. Or I don't want any carbon monoxide. I don't want any carbon dioxide. I just want soot. I want lots and lots of soot. You know, exactly how am I going to get 100% soot out of this reaction? And so since there are a lot of variables here with the pressures and whatever else, you know, what's typically done is you just play with it until you get the right product. That is, you tweak the conditions. And so there are two approaches to chemical reactions. One approach is just to try different things and see what happens. That's skeleton. And so there's lots of applications for this. For example, when they're looking for new catalysts to replace, you know, catalytic converters used to be very expensive because they had to use platinum. So rather than using platinum, which is a very expensive metal, they tried to find other suitable alternatives. Well, what's a suitable alternative? And so what they did was they would do on a little reactor plate like this big, they do 1,000 different formulations. And each one of those they test to see, do they have catalytic activity? You know? And so that was a brute force like shotgun method where they just try a whole bunch of different things and see what happens. The same thing with drug. You know, with drug discovery, they might have some kind of target molecule, and then they'll just make a whole bunch of derivatives of that, and then just try it and see what happens. And so they'll make 1,000 different variations, or 100 different variations, and see which one's most active. Then, that's the experimental approach. Then you have the theoretical approach. The theoretical approach is, they do it all on a computer and say, this is the formulation that we want, or this is the structure or molecule that we want, and then target that for synthesis and just make one. The problem is the theory is so complex that even, if the calculations predicted that to be optimal, there's so many other variables there that are difficult to incorporate into the computer program or into the math, and so they end up off a little bit. And so right now the state of the art is a mix of both. You have theory which predicts some kind of target, and then you build a whole bunch of variations around that target to see which one works best. And so for skeleton redox, I don't know what the conditions are, and the theory is quite tough, so we just try different things. You try different things, and then you analyze the products and see what you got, what you formed. And so for skeleton redox, we don't predict the products. We just mix it together and then analyze the products to figure out what happened. And so a typical skeleton redox problem would be like this here. This is in chapter 19, by the way, at the end of chapter 19. Actually, this is steps to writing skeleton redox, fruitose cover. I'm going to go through the steps. Let's just look at a problem involving skeleton redox. So rather than trying to predict what's going to happen, they just took it. They took some permanganate, which is a strong oxidizing agent, and mixed it with chloride. And when they took permanganate and chloride, it turns out they formed chlorine. The solution was acidic. They also determined that the manganese ends up as monatomic manganese 2 ion. They write the net ionic equation for the redox reaction. So in this particular case, we don't have to predict what the products are. They just mixed it together and determined what the major products are. And so what did they do? Well, they mixed permanganate with chloride. So they mixed permanganate with chloride, and under these conditions, what happened was that the permanganate ended up going to manganese 2+, and the chloride ended up going to chlorine. And so they give us the major products there, but this is not balanced, and the equation is not complete. So all we have to do is complete and balance this equation, and then we're done. So here, if the permanganate goes to manganese 2, and the chloride goes to chlorine, then we can just track what happens. This permanganate going to manganese 2 is called a half reaction. It's one half of the reaction. The other half of the reaction is the chloride goes to chlorine, so that's a half reaction. And together those make the complete reaction. But I'm going to divide it into half reactions first because this is the method that we use to determine all the other details or all the other things that are happening. And so we'll take our permanganate here and go to manganese 2 plus. That had to happen. But this is not balanced, so this is 1/2 reaction. The way we balance this is by following these steps here. So the steps are to balance all elements other than hydrogen and oxygen. Balance all elements except for hydrogen and oxygen, H and O. And so we have oxygen here, we'll ignore it. We have manganeses, we'll balance those. So on the left I have 1 manganese atom. On the right I have 1 manganese atom. This one occurs as the ion. This one occurs in the polyatomic. And so the manganese is already balanced, so we don't have to worry about that. So this is 1/2. The other half of the reaction will be chloride goes to chlorine. And so again, we do the same thing. On the left, we have 1 chlorine atom in the form of chloride. On the right, we have 2 chlorine atoms in the form of elemental chlorine. Here. So this is not balanced. Now, the way we balance it is by changing the coefficient. So if we have 1 chloride, the easy thing to do here is just multiply this by 2. Now we have 2 chlorides. And so by changing coefficient. Coefficient is what's in the front. We never change the subscript. So for example, we would never do this with a Cl sub 2 minus charge. That wouldn't be done. So we change the coefficient. All right, now it's balanced. Okay, the manganeses and the chlorines are balanced here. All right, the next step is we balance the oxygens. We balance the oxygens by adding not O2, but H2O. So we balance oxygen by adding H2O. So this is a little tricky here. So over here, permanganate contains 4 oxygens. So I'll put 4 oxygens here. Manganese 2 plus, there are no oxygens here. And so this side, I need to add 4 waters. So I'll just add 4 waters here. And so now I'm going to have manganese 2 plus 4 waters. Now the oxygens are balanced. All right, the next step here is I need to balance the hydrogens. Oh, actually, let's go to the other side here. When I look at the other side, I have no oxygens. So I have 0 oxygens on the left, 0 oxygens on the right, so it's already balanced. Okay, the next step is we need to balance hydrogen by adding H plus. So we're going to add hydrogen ion to balance out the hydrogens. So over here, I have no hydrogen because I just have 1 permanganate. But over on this side, I have how many hydrogens on the right side? Well, the manganese plus these 4 waters is going to give me a total of how many hydrogens? 8 hydrogens. And so over on the left, I have to go plus 8 H plus, and then the hydrogens will balance. Over here, there are no hydrogens on either side, so I have no hydrogens on the left, no hydrogens on the right, before it's balanced. All right, the next step is to balance the charge. When I balance the charge, the net charge on the left has to equal the net charge on the right. And if it's not equal, then we're going to balance it by adding electrons. Electrons would be negatively charged here. And so I have a -1 from the permanganate plus 8 from the hydrogen ions. So -1 plus 8 gives me plus 7. Total charge on the left. On the right, I have plus 2 from the manganese and 0 from the waters, so I'm going to get plus 2. And so the charges are not balanced. And so the way I'm going to balance the charge is by adding negative charges, the electrons. So how many electrons do I need to add here, and to what side? electrons and -1.
And the left side, you have to add it to both sides? You said it to one side.
Just one side.
You said 5 to the left side, right?
Just add 5 to the left side? That's correct. So if we had 5 electrons to the left side, then we're balanced, because this would be -5 plus 8 is +3, +3 minus 1 is +2. So +2 balances out +2, and we're balanced there. Over here, the net charge on the left, we have 2 chlorides, so that's -2, and then chlorine is neutral, so that's 0. So how do I balance this? Need to add electrons to the left side or the right side? To the right side, and how many? Yeah, 2 electrons. All right, now that's the final step. So after the final step, I combine everything. And so for the first half reaction, I have permanganate plus 8 H pluses plus 5 electrons goes to manganese 2 plus 4 H2O. If I look at this equation, it looks very familiar for me. It looks very familiar to me because it's this equation here. Permanganate plus 8 H pluses plus 5 electrons goes to manganese 2 plus 4 water. In other words, this is the half reaction where permanganate goes to manganese 2 plus. I could have saved myself some time. I didn't have to do all this. If permanganate is going to manganese 2 plus, I already have that half reaction balanced there in the redox chart. And so I could have just copied this down and skipped this entire process. In fact, this one I could, chloride and chlorine, that sounds familiar too. In fact, it's right here. 2 chlorides goes to chlorine plus 2 electrons. That's exactly what I have here. 2 chlorides goes to chlorine plus 2 electrons right here. So this one I could have copied down. So you know what? If I use the chart method, it seems like it would have given me the same. Right? But I'll talk about it in a minute. So I have my 2 half reactions here. Now the 2 half reactions have names to them. One is called the oxidation half reaction, the other is the reduction half reaction. And to remember these, we have oil rig. Oil just stands for oxidation is loss. And rig stands for reduction is gain. So which one of these is losing, which one of these is gaining? Electrons, that is. Looks like the top one is gaining or losing electrons. This one here, gaining or losing electrons? Well, this one is gaining because it's consuming the electrons as a reactant here. This one would be losing because we're going to lose. And so if this one's gaining, then this is what we call the reduction half reaction. And then down here, this must be the oxidation half reaction. In other words, what we say is that chloride was oxidized. Chloride was oxidized. If chloride was oxidized, is chloride the oxidizing agent? If chloride is oxidized, is chloride the oxidizer? No. If chloride is oxidized, then who or whom oxidized chloride? Permanganate. And so this is where a lot of confusion comes up. A lot of confusion comes up is permanganate's the reducing, no, permanganate not the reducing, permanganate is the oxidizing agent. The oxidizing agent is reduced. The reducing agent is oxidized. And so it takes some time to get those to click. It's like, you know, well, if you're the victim of something, are you the victimizer? No, the victimizer would be something else. So this is the same type of deal here that we're thinking about. So if chloride's oxidized, something else oxidized it. That something else is this. So if we call this the oxidizing agent here, the OA, and chloride must be the reducing agent here, Ra. When we have the half reactions like this is an easy time to look at the reverse reaction. If we were to go backwards here, what would this be? Well, if this is the oxidizer, then this must be the conjugate reducer. And if this is the reducer, this must be the conjugate oxidizer. And so we can see, this is useful for determining driving force here. All right. The next step here is we need to make sure the electrons gain equals the electrons lost. And so the top equation we need to multiply by 2. The bottom equation we need to multiply by 5. And that way we can get 10 electrons gained, 10 electrons lost. And so equal. And so number of electrons gained must equal the number of electrons lost. In other words, electrons have to balance. If the electrons don't balance, then something's wrong. What we're going to do is we're going to add these two up. So the reduction half reaction plus the oxidation half reaction is going to give us the net redox reaction. And so the net redox reaction is just sum up everything on the left and sum up everything on the right. So if we sum up everything on the left, I'm going to get 2 permanganates plus 16H plus 10 electrons. That's from the top equation. And then I got to account for these reactants here on the bottom equation, plus 10 chlorides. Okay, this is going to yield, now sum up everything on the right. I'm going to get 2 manganese, 2 plus 8 waters, plus 5 chlorines, plus 10 electrons, which I'll write down here. So the 10 electrons gained have to equal the 10 electrons lost. Electrons must cancel out. It's not that they don't participate, they do participate. The situation is we can't have electrons left over. You know, they would be too unstable. And we can't go buy a bottle of electrons. So we can't have electrons left over as products. And we can't have electrons left over as reactants because where do you go to get electrons? They don't sell them in a bottle. So the electrons must cancel out, which they do here. And so let's see, we'll simplify this, and then we're going to end up with 2 permanganate plus 16H plus
plus 10 chlorides yields 2 manganese 2 plus 8 H2O liquid plus 5 chlorine.
So we're pretty much told the major products. All we had to do was complete and balance it, and so this process is for completing and balancing this reaction. If we want to further analyze this reaction, then we know that this is our OA, here. This is our RA, this is our RA here going backwards, and this is our OA. And so the driving force is going from stronger to weaker. We know a driving force must be present because the reaction actually occurs. So we're going from stronger oxidizer. As permanganate and H plus is a stronger oxidizer than chlorine. You can see it here. Permanganate and H plus is a stronger oxidizer than chlorine here. So this will be a weaker oxidizer. And then chloride must be a stronger reducer than manganese in water, manganese ion in water. So chloride is a stronger reducer than manganese in water, which it is here. So this is it. And so if we were to mix permanganate and chloride, we're going to get chlorine gas. In fact, this is a common way that chlorine gas is generated in the laboratory. You just mix permanganate and chloride together. I have a little asterisk here. I have a little asterisk because it turns out this is not what we would have predicted had we done this by the chart method. The chart method would have gave us different products. So let me just talk about that briefly here. The chart method, in the chart method we inventory. And so if we have permanganate, we have chloride, we're also going to have water. Water is a potential reactant. We have other stuff, plus other stuff. Let's just say the other stuff. I don't know what it is, but there's other stuff in there. But the situation is between chloride and water. What's the strongest reducing agent on the chart? Lithium. So let's go up from lithium and we look. What is a stronger reducing agent? Water, which is here, and water here, or chloride, which is here. Yeah, water is a stronger reducing agent. And so, if there are two reducing agents present, which one's more likely to react? The water, which is the stronger, or the weaker, the chloride, which is more stable? Water. H2O from the chart. This is a stronger reducing agent. So if water is oxidized, that is, if water loses electrons, then we should form oxygen gas, not chlorine gas. So I expected this to be an oxygen generator, not a chlorine generator, because water is a more powerful reducing agent than chloride. But that's not what's observed. This is under standard conditions, and so this is the one exception you need to know. You know, I'll try to come up with an analogy for this here. You know, to oxidize chloride, you just need to strip an electron off the chlorine atom. And so an oxidizer comes along, sees an electron, just pulls it right off. Yeah. To oxidize water, what needs to happen? To oxidize water, you need to break off the hydrogens and then oxidize the oxygen. The oxygen is going from -2 here to 0 here. You got to break off the hydrogens, protons. So oxidizing water is a bit more complicated than oxidizing chloride. Oxidizing chloride, you just strip an electron off a ball, basically. Here, you got to break some bonds and arrange things. You strip an electron off a ball, and those two balls can combine together to form a molecule here, but nonetheless. So the way I think about this is like this. You know, sometimes you could get the lowest price on things, but you sacrifice a little bit of convenience. You know, you could do the more expensive thing, and it'd be a little easier, right? But if you want to save money, then you got to accept the inconvenience, right? This is, or it's like that. You know, I don't know. You could, well, anyway. So this is it. This is the cheapest one to oxidize. This is the cheapest one to oxidize. This one is a little bit more expensive to oxidize. But which one is easier to oxidize in the sense of convenience? Well, the chloride is easier. This is what we call mechanistically. Now, mechanistically, chloride is easier to oxidize. But it costs a little bit more energy to do. That's it. Well, let's say you can afford it. You know, the price difference isn't so big. If the price difference isn't so big, would you pay a little bit of extra money to make your life a little easier? Maybe, yeah. Well, nature can afford it. So what nature does is it pays a little bit of extra to oxidize the chloride instead of the water, which is more involved and more complex. And so this is the only exception you have to worry about. It's another factor because this table's based on energies. That mechanism stuff is based on something we call kinetics, and so it's a little bit different. And so another factor comes into play here. And so this is the one exception you should know. H2O versus chloride, we oxidize chloride. Instead of water. Even though water is a more powerful reducing agent according to the chart. And so using the chart method, I would have predicted we would have oxidized water and generated oxygen gas. In reality, when we do this, we oxidize chloride and generate chlorine gas. Okay, and that's the only exception. Otherwise, this chart works fine, you know, as far as predictions go. And so the chart method predicts so this is contrary to what the chart method predicts. And this is under standard conditions. We didn't tweak the conditions here. It's under normal conditions. All right, so this type of problem we didn't really have to do it with the skeleton because the chart method would have predicted the same. Well, once we know the exception with chloride versus water here, then we would have predicted the same thing using the chart method. We would have recognized that chloride's easier to oxidize than water, although it costs a little bit more energy. But what we do though is we use this to predict certain things like actually we don't use it to predict. Some things are really hard to predict. And so let's do another example here. If I take ethanol, C2H5OH, and normally when I reacted this with O2, what happens when I react ethanol with O2? Well, you say, hey, that's a combustion reaction. When ethanol reacts with O2, I should form water and CO2, right? CO2 and water. But that's not always the case because it depends on the conditions. Did I tell you about the bottle of wine I bought in Joshua Tree, town of Yucca Valley? No, I didn't tell you about that? I went camping in Joshua Tree, and so I went to Yucca Valley, which is the town, nearest big town there, to get some supplies. And so I was at the dollar store, and then there was a whole bunch of Santa Barbara wine. It was $1 a bottle. $1 a bottle for Santa Barbara wine. So I had to buy it, so I bought a bottle of it. Went back to the campsite and opened it, and then started drinking it. But I took one sip, and that was it. It was, you know what it tastes like? Vinegar. It was awful. So I ended up not drinking any of it, and then just used it to extinguish the fire at night. And then I thought, man, that was expensive. $1. At first I thought it was so cheap. Man, I'm getting such a great deal. And then I thought, what a ripoff. But anyway, so what happened was that some O2 got into the headspace, right, and then oxidized the wine, but it didn't oxidize it, or it oxidized the ethanol in the wine. And under these conditions, it oxidized it to acetic acid, which is vinegar. Acetic acid has the formula CH3COOH. How do I know? Because I tasted it. There's a very distinct odor and taste to this. And so here, there's another way of writing acetic acid, which is HC2H3O2. Acetic acid. Well, anyway, that's what happened, right? And so I don't know the exact conditions, but this is the reaction that occurred. This is a redox reaction. So it didn't oxidize my ethanol all the way to CO2. If it oxidized it to CO2, then I would have had sparkling grape juice, which would have been okay. I would have drank that, but this was awful. And so, so under these conditions, this is what happened. And so this is kind of mild conditions, mild oxidizing conditions, because if it was rigorous oxidizing conditions, I would have oxidized it completely. And so under mild oxidizing conditions, this is what happened, but this is not the complete story. And so this is skeleton redox. Skeleton redox, we try to complete the story. And so let's figure out what else happened. And so what I know for sure is that there was no more ethanol in there, and it was just vinegar. And so this is one half the reaction. And then the only thing that I could think of that could oxidize that was O2 getting past the cork, right? So the O2 must have gotten in there. And the O2 went to something else. I don't know what it went to. So let's just put a question mark here. And so this is the other half reaction there. And so the two half reactions are this here. And so why don't you finish the story for me here? I'll give you, let's do a little mini quiz to get back into the swing of things here.